Yeah, it's rough out.
So this is the exam back. Generally scores were good. There were some 90s, 80s, and so that was all promising. One of the questions on there, the one about normality and calculating probability. So the problem five, I think caught some off guard, a little bit high there, a little bit higher. And so, if you, and some people just left problem marked it blank or didn't do it, and so that knocked down some point. So instead, so you can rewrite this problem. Oh, you didn't miss any points on it, so it doesn't affect you terribly much. And if you rewrite it and submit on Wednesdays, I guess I would want to see, it would be easiest for me to see, or if you want to get things back to you. So one possibility is just to copy that page or just submit that page and then the rewrite of those problems, and I could consider, yeah.
Can you get full points back or just half?
Some portion of it. Yeah, so. I don't know if it would be full, but it would be some amount. And so, if people didn't do 2 parts of it, that could drop the score 10 points, and maybe what that one portion would be on there. If 1 or 2 people didn't answer it, I think, oh, well, they didn't know, but if a group of people didn't answer, it says, well, maybe it wasn't clear that. And so really the point is to learn the material. Understanding of it, understand what the problem is asking, and for study purposes, right? As you learn it, give you a few more points back for doing it than to be, so draconian. It's not that anybody, because of this one problem, drops so low, but instead of getting a 75, and you lost 10 points on that one, it would be closer to be more consistent, I think, with how people are doing it, the homework for a number of people. You can look at that. It won't affect everybody, but it will affect others. But in any case, not too much else to say. So in the question, number 4, I guess I was in a mood for asking questions about interpreting confidence intervals and hypotheses and comparing them. And so a number of some people mark things as inconsistent and between a couple pair of statements. Some people primarily interpreted the 2 statements. And so if people gave a proper interpretation of part of that, they could get some points along that. When I post a solution, it would have the interpretations along with the comparison. Okay. So anyway, those will be coming. The solution will be posted, and you can take a look at those. Homework is due on Friday, right? And as I said before, I'll be away, so there'll be a folder outside of my office for collecting those, and at the end of the day, the grader teaching assistant will come and get those and grade the homework. I think after today, we'll have most of the work done that you need to do, so Wednesday would be a good day for asking questions about the problem as well. Yeah.
Where is your office?
So my office, yeah, is Jean Marie 259. So back over in that corner in that direction on the second floor. And then there's my office, kind of at a bend. Here's my door. And then there's some things on the wall right there. And so there'll be a manila envelope that says Stat 140 on it. Put it in there. Okay? And so the topic today, so on Friday, we looked at comparing things with two proportions. P1 and P2. We could do 95% confidence intervals for the difference of these two things, where we would take our sample values, P1 hat minus P2 hat, plus or minus. We use normals for proportions, 1.96. And then standard errors, P1 hat over 1 minus P1 hat over N1 would be the estimate of the variance for the first one. And we add in the estimate of the variance for the second one. Make a square root of all of that. You get a confidence interval for the difference of two proportions. If we want to do hypothesis testing, we can test whether these two things are the same or not. And then the alternative is that they're not the same. And in this case, we calculate a composite. If that's really the case, when we want to test whether that's true, we're first going to assume that it's true and compute a composite version, which if you have the count N1, X1 and X2, you can just use those, combine everything and get a sample proportion. And then our Z statistic for testing the difference between our sample proportions, and we divide it by P hat, 1 minus P hat, over the sample size. And then we add in the same thing over N2. And so that becomes our statistic. And if that is large, if that's bigger than 1.96 or less than negative 1.96, we've got the two sample versions of the one sample thing that we had before. But you often don't have just two groups you're comparing. In randomized studies, you often have multiple treatment groups. You're considering a couple different options. One study is in the diabetes literature that's going on, called the GRADE study, is comparing up to 6 different treatments that go along with the primary drug treatment of metformin. So there's 6 different outcomes. And the type of questions that we're going to ask is, did somebody after 3 years of treatment become diabetic or not, if they were kind of on the verge? Right? So there's kind of a yes or no outcome on several different groups. And so today, two or more proportions. And also relevant for what are called two-way tables. So in the example that's in the handout today, right, is a fast testing genotypes for muscle types. And so there's a classification. Some people are control. There's some sprinters and some endurance athletes. Sprint, endurance, athletes there. and they take 436 individuals as their control. They have 107 sprint athletes, 194 endurance. Total sample size that we have is 737. I'll label that N. And they do the genetic testing on these different individuals, on some genes related to muscles. And the genotypes are RR, RS, and XX, related to whether they're fast muscles or a certain type. And so they get 130 as the count here, 226, 80 in that row. This row is 53, 48, and 6. And in this row, it's 60, 88, 46. And if you add going down the columns, there's 243 that have the RR genetic type. And adding down, there's 362 here and 132. And so a basic question is having certain muscle types associated with these groups, right? And there could be a couple things going on, right? Maybe probably being in one of these groups doesn't, I don't know, it's not a clear causation thing. Do people enter these groups because they have these muscle types, or is they more likely to be successful, so they stay in it? Or do they have these muscle types kind of lead them into that, or do they, if they're doing this, whatever, there's kind of a biological thing going on. But are these associated? Right? It's the basic question. One of these variables, by the variables I mean gene type, genetic type, and then group status over there, athlete status, associated. And so to do this, we can, one way to do this is called a chi-square test. And so we have a null hypothesis that these things are independent of one another. There's no association. So again, our null hypothesis is no association, no effect, no difference. Another way of phrasing that is, well, let's write that down. So our null hypothesis is that there's no association, no difference by group, meaning that the rate, no difference in proportion by group. The alternative is that there is some type of association. And the probabilities of being in these different athlete groups changes by genetic type, or viewed the other way, that the genetic type changes by athlete status, right? So if that's our table, and if there's no association, under this, we're going to calculate probabilities. We're going to interpret this as the probabilities are the same by row in each column. Or you might let rows and columns and view it the other way, where the probabilities can be the same. By column, right, in each row. So the percentage of people that have each genetic type is the same, no matter whether you're an athlete or an endurance athlete or that. So we're going to use our sample data to calculate that, and then calculate how many we would expect under the null hypothesis. So we calculate an expected number. hypotheses and these things about those, if it's kind of a binomial experiment, we have enough information to actually calculate expected value. So we're going to write that on the next page, do the calculation. Put that up here. So we had our original table. Out here is 130, 226, right again, 53, 48, 6, and then 60, 88, 46. And in this row down here, as you add those down, was 243, 62, and 132. Those are the same numbers. This is the RR, RX, and XX. The total sample size was 737. So the proportion that's in here, the p hat for x-axis are 243 over 737. The p hat for Rx was the 362 over 737. And p hat for R, am I doing it right? This one was RR, sorry. RR, this was XX over here, is the 132 over 737. So if that proportion, RR, applies to every single row, right, so what's that? What are those numbers? I was trying to see if I brought some other example written out, so it's not as useful for this, but so I guess I have to do a little bit of computer. You get those proportions. So we want the 243 over 737 and 362 over 737 and 132 over 737. You get those proportions in there. So about 0.33, 0.49, and the last one 0.18. They almost rounded, no, they rounded. 2 rounds, 0.33. Yeah, that adds up to 1. Right. And so in this row, there were 436 in that one. So if those are constant, we would expect 436 times 33 to be in that cell. So we have expected numbers. So if there's 436 over here, kind of an interesting dynamic, making the table small and then you write it and then it becomes that big. Right? So if you take the 436 times the, I'll make this one do it a little bit wider here. You can see it. We take the 436 times the 0.33 from this. Right? Overall, it's 33%. So if it's independent, we'd expect 33% up here. And we have 436 total times the 49% were in this column. So it should apply to that one if it's independent, not any different. Right? And then 436 times the last one, 0.18. So those are going to calculate some expected values. Right? How are we going to do that for all 3 rows? So there are 107 here. So if these proportions, if these rates are the same in that one, 107 times 0.33, 107 times 0.49, and 107 times 0.18. And then this other one had 194, 107, 194. It would be 194 times that rate. 194 times 7.49, 194 times 0.18. Those will give us expected values. And those expected values, I do have these. So the expected, I'll write these in red. So we're going to stand out 143.76. And you can keep these as decimals. Maybe one decimal place would be enough, but the chart you have has two. These do not have to be rounded. 38.9. And 33% of 107 is a little bit more than 33. It's 35.28. That's about half of 107, so we've got 53. It's 52.56. 18%, 100 would be 18. Just a little bit more, 19.16. And then a third of 194 is 243. It's 63.96. And 95.29. And this one is 34.75. Those are our expected values under, these are expected. We have no association. How do those compare to the real data?
They're pretty close.
Many times they're close. Some ways, right? 60, almost 64, that's pretty close. But there's a few differences, right? 130, 143, 226, 214. So there's some differences. So it's not totally consistent. I mean, it could be closer. And so then this is the question we ask: is this a surprising result? Is this an extreme result if it really was supposed to be equal? Right? It was supposed to be really, if this is really as accurate, and that those expected values under no association really are accurate, is this something that would happen by chance? Is it going to give us a p-value, a probability of happening under that null hypothesis that's very large? Is it something rare? Have we seen something strange? Right? If it's strange, and we decide these are too far away, just like always p1 hat minus p2 hat, if those things are too far away relative to the standard errors, then it's surprising. And so how do you do this? We want to look at all the information all together. So what could you do? You can take differences. Negative 13, that would be a difference of about 12. That's a difference of 2. That's pretty close. Right? So you have all these differences. Some are positive, some are negative. Right? If you add them together, they'll cancel out. So you can't just take the differences and add them, because they actually would add it to 0. But, so you need to do something else, right? So we're going to square. We're going to square the differences. So we're going to take 130 minus 143.76, so negative 13.76, and square it. But something's happening as well. You get bigger tables. If the tables add up to just 100, you're not going to differ by more than a few counts, probably. Right? But if the table added up to 1,000, you can easily differ by 10. Right? As it gets bigger, so we need to standardize. We kind of need to z-score it. So we're going to square it, and the thing that we do is divide by the expected value. As that expected value is getting bigger, kind of a small deviation is no longer so important. Right? It has to be a big deviation from a big thing like that. So we have something called an x squared statistic, or chi-squared statistic. The Greek letter is, for the distribution, is chi. It's a sum over all cells in the table. So in this case, we have a 3 by 3 table, which is about as big as we do by hand, of the thing that we add over is the observed value minus the expected value squared, and that being divided by the expected value. So we end up adding 9 things together. So in the first cell, we had 130. And we computed that we expected 143.76. We're going to square that divided by 143.76. So that number is to be 1.316. Is the information that's given on the chart there. All right, then moving over to the next one, the observed number was 226. We expected under that model, we observed 226 and we expected 214. So we're going to subtract that, square it, and then divide by 214. Minus 214.15 squared over 214.15. And that contribution, according to the table, is 0.655. I keep going all the way through all 9 of them. So 3 by 3 is about as big as we'll do by hand. It takes, right? Portions, 9 expected values, 9 contributions to the sum of squared. And the last one in that is the endurance XX. So 46 minus 34.75 squared over 34.75. And that contribution by itself is 3.645. So this one had a difference of about 8. No, it's a difference more like 11, right? Almost 12. 11 squared is 121. 121 divided by 30 is a little more than 3. Right? So that's a contribution there. Right? So this all adds up to a value of, it's a statistic value of 24.805. And that's our chi-square statistic value. Now, we compare that to a chi-square distribution, because in large samples, this thing has a distribution that looks like that. So, if this is large, we're going to reject the null hypothesis and conclude that there is some association there. A significant association, more than just random chance. Right? Why do we care if it's large? Well, everything's positive. We squared everything, so everything is, if it was exactly, if we had 130 expected, we'd get 0. We're not going to get below 0. And if we had 131, that'd be awfully close. Yeah.
Would it also work if we had a large negative number?
So in this case, so this is what the thing is negative, so we're squaring it.
Oh, so it'd just be positive then?
Yep. Yeah, everything comes out to be positive. Yeah. The fact of squaring it puts it all on positive. And so chi-square is the Greek chi-square. Chi with a square on it, with a certain degrees of freedom. It's a distribution that kind of looks like this. This is our chi-square distribution. And our statistic, our x squared, we're going to put on here. And if our x squared, here's at 0. If our x squared is far enough out here, if that area is less than, we have some tail area here, 0.05. And if it's out beyond that, if it's far enough out there, we're going to reject. So, this is our book for the tables. I guess it has a 0.95 column for that. So we're going to reject the null hypothesis if our x squared statistic is big. It's greater than the chi-square with the right degrees of freedom, 0.95. And the degrees of freedom changes depending on the size of the table. Rows -1, columns -1. So in this case, 3 minus 1 times 3 minus 1 is 2 times 2 is 4. So we're going to look at a chi-square 4 as a cutoff. And so in the table that's copied for you, the Rosman version of the table, right, there's a degrees of freedom equals 4, and look out that until the 0.95 column, and it's 9.49. And our x squared statistic we got, in this case, is 24. So we drew a picture kind of for this one, it would be, here's our 9.49. And if we're out past that, we're going to reject, we're out here. Well, it's really unusual if these things are. If I could draw it nicely, this would kind of keep sloping down to where it gets really, really tiny. It's a tiny chance where we get something as imbalanced as this and away from our null hypothesis. So we reject null hypothesis. It's clear that there is some type of an association. It's a little bit more involved, right? As we've gone through these procedures, the statistics get more involved, but a lot of the logic is the same. Right? Null hypothesis, there's no association. So the rates, the proportions are the same by rows, by columns. And we can calculate expected values. In this case, we calculated these percentages and then divided the row numbers 436, 107 across these by those proportions to get expected values. Compare all the observed counts to all the expected values. And we did it by squaring the difference and divided by the expected. Standardize it. Add those up and large samples and has this chi-square distribution, which is calculated, so we can compare. How about a second example? Well, that's athletes. There's a there seems to be a significant difference there. Are those people athletes because they have the genetics, or it's kind of a complex question. Maybe it gave them a muscle advantage, so they were good at it, so they stayed at it, and what exactly is going on? But it's kind of interesting. See, there was an article the other day in the newspaper about heart sizes and athletes. Runners, rowers, swimmers have different heart sizes than people who are not better than. It's a muscle, you use it, it gets stronger, it gets thicker, it gets bigger, and it pumps more efficiently. Right? So there's a real, but this was saying that there's a difference between runners and swimmers in terms of that. The runners seem to have a little bit more strength in their heart, and the hypothesis for a difference was that the swimmers are buoyant and horizontal, right? And you have to pump blood this way versus pumping blood this way. So there seemed to be some difference. So it was kind of interesting. So it doesn't necessarily mean that the differences in hearts cause them to be different types of runners, or it could be caused a result of that. But this genetics is kind of a little bit before that, rather than the result of that activity. But it's kind of related. So on the next one, what about gender classified? There's male and female, and these genetics. And so here is the table. And in here, male and female. And if they had enough data, they could add other categories, but this is what we have right now. 134. Males turning into females. I don't know why the study is unequal that way. That would be another question. Are these volunteers? So is it getting that? But even if it's different, 426, you can still test, is there an association? And so the basic hypothesis we want to study question, is there an association? Genetic type and gender. And these are the counts: 40, 73, 21, 88, 147, 57. And so this is 128, 140. Right, or 220 down there, 220 and 78 are the counts in that way. We could count, we could do it the other way. We could count what's the percentage that are male, what's the percentage that are female. $134 over 426 are male, 292 out of 426 are female. And if you have those percentages, 134 out of 46, 0.315, say, 0.685 for that. And so if there's no association, you'd expect the same percentage of males versus females in every genetic category. You expect that 128 to be divided 31.5%, 68%. You'd expect the 220 to be divided the same percentage without any difference, right? So expected values, so for instance here, we'd expect under no association. So there's 290, well, let's see, there's 128 RRs. And we'd expect 0.685 to be female, right, out of that. So that number in there would be 87.74. And I'll squeeze in here if we get all, see it together. The expected numbers, 40. Uh, 40.26. By the way, better on this side. 69.20, These are in the table, the chart there. 87.74, 150, 53.46. How do those look in comparison to the actual counts? Those look pretty close, right? At least more so than the other ones, right? There's a difference of 0.26, a difference of just about 4, difference of 3.5, difference of less than 1, difference of about 3, almost 4. Those are kind of smaller magnitude differences. And so then if you do the chi-square statistic, as described there, the chi-square value is 1.50. Degrees of freedom we use, again, rows minus 1. Columns minus 1. So there's only 2 rows this time. If I list the total row, don't count that in terms of the total number of rows. Right, if I did males, females, total, just there's only 2 really. So there's 2 degrees of freedom. It keeps changing because you get bigger tables, you're adding more things together. So you're likely to get bigger values. Chi-square 2, I think still looks kind of like this. On our table, we can look up the chi-square 2 to 0.95. What's the 95% cutoff value this time? You see it there?
It's like 7.38.
Not quite. That's 7.38 is under the 0.975 column. This one, everything's squared, so we are looking at the 95% value. When it was just the normal, we could have either the bigger or the smaller, then we do it.
It's one side.
This one is one side because we've squared everything, so everything being away from the null hypothesis means a big value, and that's it. So under the 0.95, right, you see the 5.99 value there. So 5.99 is somewhere about out here with 5% up here. And we're back at 1. Right? It's not 0. It's very hard to get 0, because that means you basically have to match exactly. But 1 is low variability. It's not very far away. So in this case, do not reject. There might be no association. So between male, female, and the genetic variable, you know, if it's not sex linked, if it's not on that, on the chromosomes that are differed by sex, it doesn't seem to have been reproduced over generations, and it seems to be kind of balanced. So that's what we can do for groups. But any questions about it? Some of these things can be done in R. On your assignment, you do a little bit by hand, just to show calculating rates, calculating expected values, calculating statistics, to get a clear indication of it. Which over would be a nice a small example. But any questions before we get another one? We'll look at one other little example. So in this study, in a study of looking at treatments for cocaine addiction, had a number of volunteers in that study. Some were given desipramine as an active ingredient, others were given lithium, others were given a placebo. The total number, 24 were in each group, for a total of 72 in the study. And then they asked, did they relapse or not within a certain time frame. If they relapse, go out and start using drugs again. 10 in the desipramine group did, 18 and then 20 on placebo. So 48 had relapse. No relapse, 14, 6. This is just subtracting to get these other numbers. 4, so 24 relapse. Cocaine addiction, like a lot of addictions, treatments are very poor, don't work so well, very low rate of success. Is there a difference between these groups? Does one or more treatment methods seem to perform better, or are they all just kind of equal? Is there a better treatment? Well, if we started with the study with 3 groups, you could test desipramine versus placebo. The placebo kind of recommended things to do kind of overall test. Is there any difference out there? People generally were expected to do a high squared test. So it's 10 out of 24. What do I record? Or 42% relapse here. 18 out of 24 is 75% relapse. 20 out of 24 is 0.83% relapse. We also need the overall one. That will be useful for thinking about proportions. So 48 out of 72 is 0.67. So if we had the same rate of relapse, if we had 67% relapse in every single group, we would expect 67% to apply to this 24, and to this 24, and to this 67% is 16 and 8, 16 and 8, 16 and 8. These would be the expected if relapse, if the percentage of relapse is 0.67. Look like it matches that. pretty well, or some pretty big differences. Yeah.
There's a large difference.
There's some pretty big differences, kind of as small numbers overall smaller than those other examples, but there's pretty big percentage differences. So is it statistically significant? I'm not going to fit it on that. But we calculate the x squared to take this, what you observe minus expected. I can write all these out. 10 minus 16 squared over 16. I get that first row, and 14 minus 8 squared over 8. That's the first row. So 10 minus 16 squared over 16, 14 minus 8 squared over 8. Right. That's that first contribution there. The next one adds in 18 minus 16 squared over 16. This one then 6 minus 8 squared over 8. The last row had 20 minus 16 squared over 16, and 4 minus 8 squared over 8. And so all of these contributions, this is 2.25. This one is a big contribution, right? 6 squared is 36 over 8. That's pretty out of balance. That adds in 4.5. The next two rows add in 0.25 and 0.5. Not all that discrepant. And 1 and 2. So this all adds up to 10.5, which is a pretty big value. We would use degrees of freedom. 3 minus 1, 2 minus 1 gives 2. And just like the last problem, the chi-square with 2 degrees of freedom, the 95 tail up there was the 5.99. So we're beyond that. There's a statistically significant association. If you keep track of what you're calculating, even doing a few of these by hand doesn't have to take too much, but it does take some careful, which row and column are you dealing with, and so check it out. In R, there's a chi-square.test command. This is named after Egon Pearson, or there's a couple Pearsons that set up biometric societies in England and describe these tests and apply different data. This is a chi-square test, performs this test. It's also called the goodness of fit test. It's the different name, the chi-square test. It wants x and y. X is Newman-Farad vector. So how does it go again? It's a matrix with one row or one column. I'm just trying to remember 2 rows. 2 dimensions. So we just need to put a table, right? So X here is, we want a little matrix. And there's code on the assignment to help you set this up. So in R, there's 10 and 14, those are our first 2 values, then 8 and 6, and then 20 and 4. And we want this matrix that has 3 rows, and we want 10, 14, and then across by row, doing it by row, this sets it up, right? So here's X. X is our little matrix of counts. And then this chi-square dot test, I just put X in there. I'm going to take out there's a correction. You know, our book has all these little things, add 1/2 here, add 1/2 there to make things more accurate. And this correction, it's a correction for continuity, because we have counts here, integers, but our chi-square distribution is a nice smooth curve. This helps out a little bit. But let's put it like this. And you just run that, and it does the chi-squared, and it gives you this 10.5 value. Degrees of freedom 2, p-value, so this is the probability that, okay, so 1 minus the chi-squared 10.5, 2, big little arc there. That p chi-squared is the probability you're less than a value. So the chance that you're less than 10.5 for a chi-square with 2 degrees of freedom is about 0.995. So 1 minus the probability is bigger. So that value comes from a calculation like that. And this is our chi-square statistic. And because that p-value is very, very small, we reject the hypothesis. It does not appear to be independent. So there is a difference. One of those drugs that seems to certainly work better. Out of this, there's extra things that it computes as part of doing this. It's all stored there kind of behind the scenes. And so it has expected values. I remember they were 67% relapse, 33% not relapse. And so 24 in each group, so it was even split. These are the expected values. And so a full answer, right, would give a statistical significance, but also compare where are the differences. You might have extra things in there. Let's see. This is a list of things, so there's extra stuff on there. There's statistics, p-value, observed, expected residuals, standardized residuals. I think the standardized residuals squared are how things contribute no, that's not how things contribute to that. But anyways, you could look at this a little bit more, and there's different residuals. Here, this is how they're different. Maybe residual squared this is what it added into the chi-square statistic. So kind of, if you wanted to do that, you could find, I don't ask you to do that, but there's kind of the extra elements of the computation are stuck in there. In the R help commands, it gives these different things that it gives out. If you don't use the corrected version of this, so the default is that correct equals true. It does a continuity correction. It does the same chi-square statistic, and now the p-value is that different at all? No, it didn't even change it. No. Correction equals true or correction equals false. Maybe it's not the right command. Correct. Yeah, so that is an option there. So it doesn't seem to change it in this particular case. So it might just balance out, so it just ends up being about the same, but it could change it just a little bit. Same thing. Sometimes if you have real small sample sizes or one of those cells that has a real small expected value, you might want to check that and see if it changes it very much. If things are really significant, like 0.005, it's not going to make it go to 0.4 or something. It's going to change it a little bit. If you have p-values at around 0.04, well, it might swing it to 0.05, 0.06, and you kind of right at that boundary. You kind of fair reporting to give both. And it's easy to compute both. So that's chi-square. It's a few more steps, right? But keep in mind that no association means constant rates for all groups, and you kind of go through the steps. All right.
Thank you.
Yep.
Jim Sharp.
Yep, you too. Everyone, Jane.
Hold on a second, just
Yeah.
I'm sorry about this. I'm just lowest freaking test taker, and I know how to do these.
Yeah.
Like I'm just that I didn't have the time to finish what was on me. Is there anything I can do to make up
But I
some of
did,
this?
I sent a note. Did you
Yes,
email?
I just got that
So,
like not too long ago.
but so if you rewrite these and just
Okay.
hand them in on on Wednesday.
Okay.
So you can get some credit for those. I did-
Both of these?
Yep.
Okay, thank you so much.
Yep.
I know how to do that.
Yeah,
That's what hurts me the most.
and you've done some of that work on assignments and things like that. So write those up and hand them in.
Okay.
And you'll get at least, some credit back. So if I give you half for that, you don't get
I-
Wait.
Thank you so much. I appreciate
Sure.
it. I know how to do it. That's the hardest part for me. But I appreciate your help.
Do you often have time issues with testing?
Yes,
Yeah.
I had a test
So-
this morning.
So, some students get, a designation of having a test taking difference and get extra time. And so I've had students in almost every, not this class this time, but in most of my other classes, there's been one or two students who have that and they get time and a half. And it's a very natural process here because the college, authorizes it, they send me a note, the instructor doesn't have to make a decision, it's the recommended situation.
Definitely.
And sometimes, and so you can take it in the library. It's a busy place over there for a lot of people doing that. And so then you get time and a half, and it gives you the chance to show what you know.
I was in the same program at my
Yeah.
boarding school. It was they would just give me a little extra time to
Yeah.
like
So,
the library. It was the same situation.
even for the final, if they would authorize that before that time, getting a time and a half on the final could show a big difference.
Definitely. No, I definitely agree. Thank you.
All right, just
Appreciate it.
something to check into.
Of course. No, I definitely will. Thank you very much.
Yeah,
Have a good day.
you too.